Okay, welcome to section 7.3, logarithmic functions as inverses. And you're probably thinking, well, the inverse of what? Well, recently we've been working with exponential expressions, and those expressions have looked very similar to what we have here, y equals a b to the x, where you've got this base and an exponent and a value, and maybe something multiplied out front, like an initial value or some kind of stretch or compression for your graphs. This idea is very similar to what we have here, where you have a base raised to some exponent equaling some value. This here is exponential. This here is what they call logarithmic, where you're taking a log base b of x equals the exponent. And this would be very good notes for your Cornell note-taking system right here. Cornell. Also make sure in your Cornell notes that you've got these objectives down. Let's take a look at writing a logarithmic function from an exponential equation. 100 equals 10 squared. Well, as before, we had some type of exponential expression, y equals b to the x, where we've got the exponent here, your base here, equaling some value. So if we write that in this format, and I know it's kind of switched up with this, what they have right here, but again, the idea really is having a base, an exponent, and a value. So let's go ahead and write our log, which is short for logarithm, and our base. What's our base up here? Well, 10 is the base for this exponent, so I'm going to write log base 10. Down here, it's like a low subscript number. Log base 10 of 100 equals the exponent of 2. So if you want to look at it like this, you could have log base value equals the exponent. All logarithms are exponents. That's all that they are. It's a different way of writing exponents. And if you recall, you've probably seen numerous problems where we've had something like y equals 2 to the x plus 1, maybe minus 3 or something like that, showing some translations. Well, we've never been able to solve for x. We've only been able to graph it when it gets to a certain point. Well, now we're going to learn these next few chapters on how to rewrite this exponent as a logarithm, and then learn how to work with the logarithm so that we can actually solve for x. Let's take a look at our next one here. 81 equals 3/4, and you'll see that they had 81 as the value, 3 as the base, and 4 as the exponent. Remember, log base value equals exponent. So let's take a look at these three examples right here. I'm going to try and blow these up a little bit. There we go. And then solve each one. First one, let's write this as, what is the logarithmic form of this equation? We're first going to write log, and then our base. Our base is 6. Our value is 36. And our exponent, in other words, what is the log equal to, is 2. Here, we might have a little bit more work to do. We want to write this as a logarithmic form. We have log base 2/3 equals our value, 8/27, equals our exponent of 3. Log base value equals the exponent. Base value exponent. So let's take a look at the last one. our base is 3, our value is 1, and it's always equal to the exponent of 0. Now let's take a look at finding the value of logarithms. In other words, how do we work backwards from something that's in logarithmic form now into exponential form and then into a simple form that we can solve for x. Let's take a look at our first one. We have log base x, log base 8, 32 equals x. So in other words, 8 is going to have an exponent of x, which it does right here, and it's going to equal the value. Now, they went ahead and rewrote these two values, 32 and 8, so that they have the same base. If they have the same base, like they do right here, the property of exponents, the power property, allows you to say if the bases are the same, we can set the exponents equal to each other and solve for x. As long as the bases are the same, the exponents are the same. So now that they rewrote this 2 to the 5th, which is 32, and 2 to the 3rd, which is 8, they went ahead and dropped the bases and just set the exponents equal to each other, and then solved for x. Divided both sides by 3, and there is your value for x. Again, they went ahead and rewrote this from a logarithmic to an exponential expression. 8 to the x equals 32. Then rewrote each base so that the bases were wrote each value so that the bases were the same. Then set each exponent equal to each other. Then solve for x. So let's take a look at these three right here. What is the value of each logarithm? All right, I'm going to go ahead and use some special technology here. When you see these logarithms, they're written just like this, log base 5, 125. Well, they don't really give you or show you the exponent. So magically, mysteriously, they expect you to say, all right, this log base 5, 125 is equal to some variable. But they don't write it like that. Don't ask me why, but you should really understand that there is actually an x right here. Even though it's not written, there really is one here. So now let's take a look at solving this here. Log base 5, so the base is 5. My exponent is x, even though we can't see it, and it's going to equal 125. Well, you may ask yourself, what exponent for 5 would make this 125? So 5 to what power equals 125? Some of you might quickly remember that 5 to the 3rd is equal to 125. Therefore, x is going to equal 3. But let's say you didn't know that, and you decided, well, let's go ahead and use that property of exponents and write this. This is as base as it gets, and you're going to write this in the most basic form. This is 5 to the 3rd, and then say, since the bases are the same, set the exponents equal to each other. And x is still equal to 3. Next one. We still have that imaginary x over here. Sometimes I suggest people to go ahead and just write it in. Anytime they see a logarithm, just write in equals x, just to remind them what to solve for. So you're going to have 4 to the x equals 32. Now, if you didn't know that 4 to some power was equal to 32, you could sit there and think, well, let's go ahead and rewrite both these numbers in their most basic form. Well, 4 can be written as 2 to the 2nd, and 2 is your most basic base, and that's going to be raised all to the x. And then you can rewrite 32 as 2, the most basic base, to some power. Well, 2 to the 3rd is 8, 2 to the 4th is 16, and 2 to the 5th is equal to 32. Now over here, when you have a power to a power, you multiply the exponents. And here, you're going to use the exponent of 5, since the bases are the same, and then solve for x. Last one here, again, we've got that, I'm going to use that magic pen over here, just to show you that it does equal x. And I'm going to have 64 to the x, there it goes, equals the value of 1/32. So let's go ahead and think about this one for a second. I'm going to rewrite 64 in its most basic base. And if you recall, there were a couple numbers, especially 2, that comes in awfully handy when writing logarithms. We said over here that 2 to the 5th was 32, so this is probably going to be 2 to the 6th. And then I'm going to write this as 1 to the 2 to the 5th. Now, over here, power to power, you multiply the exponents. And here, if you remember, with exponents, is that this is really the inverse of 2 to the 5th. So I can rewrite this as 2 to the negative 5, because the negative makes you flip it, and then you keep the exponent right here. So now that I have the same bases, I'm going to set them equal to each other. 6x, the exponents equal to each other. And now you're going to have x equals negative 5/6. All right, that should help you out with logarithms on the first section of this inverses of exponential expressions, otherwise known as logarithms. And we'll have the other half talking about common logarithms tomorrow. Thanks for listening.